A projectile is launched with a speed of v0 at an angle of beta plus gamma with respect to the incline in a downward projection. The angle of the incline is beta. Just as this projectile is launched, another ball is released from the same position at the top of the incline at the same time. Let's watch that in motion. The projectile is launched and the ball is released at exactly the same time. And it so happens that the projectile lands exactly on the moving ball. Let's watch it again. For this to happen, what should be the relationship between the angles beta and gamma? Be careful here. Gamma is not the angle of launch. The angle of launch is beta plus gamma with respect to the incline. We've rotated the coordinate system such that the x-axis lies along the plane of the incline. For this to happen, since both the projectile and the ball start together and then they meet, they would have covered exactly the same x displacement during the time of flight of the projectile. And remember here that the x-axis is not the horizontal axis, but the one along the plane of the incline. Let's find the x displacement of the projectile first. And we do that by applying the second equation of motion along the x-axis. Be very careful with the signs here. The initial x displacement is 0. The final x displacement is minus x, minus since it is in the negative x direction. The initial velocity is minus v0 cos of beta plus gamma, and this too is negative since it is along the negative direction of the x-axis. The acceleration is minus g sine beta, and that too points in the negative direction of the x-axis. And since this is a downward projection, you can see that the initial velocity and the acceleration are both in the same direction, that is along the negative x direction. And let t be the time of flight of the projectile, so the time it takes from launch to landing. So right from the time it is launched to the time it lands back on the incline. These values are now plugged into the second equation of motion along the x direction, and this is our first equation. Let's do the same for the ball which slides down. We apply the second equation of motion along the x-axis. The initial x displacement is 0, and the final x displacement is minus x since it is in the negative x direction. The initial velocity is 0 since the ball begins from rest. The acceleration is minus g sine beta, and that points in the negative direction of the x-axis. And t is the time of flight of the projectile, which is the same time that the ball also slides down before meeting the projectile. And all these values go into the second equation of motion along the x-axis, which gives us equation 2. If we compare both these equations 1 and 2, we find that the left-hand side is the same, minus x minus 0, and the second term of the right-hand side is also the same, minus half g sine beta t squared. And the time t is the same for both equations, that is the time from the launch all the way to the landing, which implies that the first terms of the right-hand side, colored in red, should be the same. So V0 cos of beta plus gamma times t should be equal to 0. Now V0 is greater than 0, and the time t is also greater than 0, which implies that cos of beta plus gamma must necessarily be 0. If cos of beta plus gamma is 0, then beta plus gamma must be 90 degrees. And if beta plus gamma is 90 degrees, it must mean that the projectile is launched vertically from the plane of the incline or at right angles to the plane of the incline. When you think about it though, it is very logical. When a projectile is launched at 90 degrees with the incline, it will not have an initial velocity component along the x-axis or along the plane of the incline. So its initial velocity along the x direction will be 0. The ball is released from rest, and its initial velocity would also be 0 along any axis, or in this case, along the plane of the incline. So along the plane of the incline, both the projectile and the ball have no initial velocity component along the x-axis, and they both have the same acceleration g sine beta along the plane of the incline. So their x displacements or displacements along the incline at all times should be identical, and therefore when the projectile lands back on the incline, the ball would have also had the same displacement along the incline and they would meet. Let's try out different points in the trajectory. And you can see that if we draw a vertical line about the incline through the blue ball, we will always find the projectile also lying on that same line, meaning that their x displacements are always the same at all times. If a projectile is launched down an incline and has an initial velocity component equal to the initial speed of a ball thrown down along the incline, the projectile and the ball would meet at some point lower down on the incline. This would happen since their initial velocities along the incline are the same, and their acceleration along the plane of the incline would also be identical.